Should I start?
Just a second. I'm gonna introduce you a little bit. So there is a short biography of Dr. Sarnat. Dr. Sarnat is nowadays is a postdoctoral research here in the University of São Paulo. His study is funded by Petrobras. Um, he earned his PhD from the Indian Institute of Technology, Madras, where he research focused on phase field modeling of fracture and fatigue in multi-phase composites. He's currently working here with us, working on the phase field fracture framework in implementation into Abaqus through UL subroutine, coupled with UMAT subroutine, to simulate hydrogen-assisted ductal fracture under complex stress state. His expertise spans computational mechanics, fractal mechanics, fatigue, and finite element method, with several peer-reviewed journal publications and international conference as well. Okay, so Sarnat, please, you can start your presentation.
First, let me share my slide.
So I say I am recording the presentation, so I can share it later with you as well.
I hope everyone can see the screen, right?
Yeah, we can see it.
Okay. So thank you for coming to this talk. My name is Thauram Sarnat. I am a postdoctoral researcher working under Diego Felipe Sarjosa in the Department of Ocean and Naval Architecture. So today I would like to give some introduction on the phase field method of fracture using the Abaqus software. So fracture is an important phenomena that occurs in every structure. It may be buildings, it may be bridges, it may be any automobile structures. So fracture material fails because of the fracture, and in some structures such as offshore structures that is shown in the figure. So these structures are exposed to the hydrogen-rich environment, which can also degrade the toughness of the material, and the fracture occurs in a very in a very fast manner, so which can cause very expensive damage to the structure. So here we are trying to understand the fracture mechanism using the computational fracture mechanics. Computational fracture mechanics can be classified as discontinuous approach and the continuous approach. So in the discontinuous approach, fracture is a discontinuity in the material, and such a discontinuity is represented by a sharp function. So here we have a sharp function, and at the point where there is crack, the value of this function is 1. So this continuous crack is represented by using such function, whereas in a continuous approach, a crack is represented by a smooth function. So what is a smooth function? In a smooth function, there is a smooth transition from this phi equal to 0 to 1. In the case of the discontinuous approach, here uh, here if you look here, the value of this d is 0, and at the point where the crack is located, the value of d is 1. So here the d and the phi are same. I'm sorry for this mistake. So the phi and the d, they are same. They represent the same thing, but In the case of the continuous approach, the phi is a smooth function. So there are some certain advantages for using this the smooth function. And what are the advantages of using the smooth function, which we'll see in the upcoming slides. So the takeaway from this slide is that in the continuous approach, we represent the crack using the smooth function. And the continuous approach that we are going to look at is the phase fill method. So why we are using the phase fill method? In the phase fill method, the crack initiation, crack propagation, crack merging, crack branching, all this can be achieved without having any ad hoc criteria. So what I mean by is that the crack initiation, propagation, merging, and the branching are governed by the minimization of the energy functional. This minimization of the energy functional we'll see in the upcoming slide. And also, because of using the smooth function, we don't need to track the crack part. In the discontinuous approach, we need to know the crack surface area, but in this approach, we don't need to know the crack surface area. So that is one advantage of this function. And especially when we have a very complex cracks in the 2D and the 3D structure, when we have a very complex crack, this method is very good because it is very difficult to track the crack part when we have a very complex crack system. So these are the advantages of using the phase fill method. Now let's look at what is the smooth function. So as I have said earlier, in a sharp crack, this rod has a sharp crack at its center, and this is represented by using a sharp function or a discrete function by using this kind of function. And in the case of a smeared crack, or the smooth crack, where the crack is diffuse into the surrounding region. So the damage is sort of diffuse into the surrounding region. So such a damage is represented by this kind of function. So where there is a smooth transition from phi equal to 0 to 1. And this is the point where where the crack is located, but because it is sort of diffuse, so this is the crack region. So what kind of smooth function we can use to represent the smeared crack? So we need to have the condition like at x equal to 0, the value of phi is 1, and at very far away distance like here, phi is 0. So from phi equal to 0 to 1, there is this smooth transition. So this kind of function can be represented by this function e to the power minus mod of x divided by L. This is not the only function. We can use other functions also, provided that they have to satisfy this condition. At x equal to 0, phi is 1, and x equal to plus minus infinity, phi is 0. So this function is very commonly used in many of the literature. So we can also come up with other function. For my work, I have used this function. So using this smooth function. Now, first, let's look at the potential energy of a solid. So when we talk about a solid where a load is applied, so the total potential energy of a solid is the internal energy stored in the solid minus the external work done. And what is this internal energy of a solid? This is the elastic energy stored in the material plus the energy associated with the formation of the crack. So you can think of this as the dissipated energy due to the formation of the crack. So this total comprises the total internal energy in the material. And remember, this is the this is the total potential energy. So this is the internal energy minus the external work done. And here GC is the critical energy release rate. This is the energy required per unit extension of crack per unit thickness. This is obtained from the Griffith's energy balance. This representation is using the sharp crack. Now, by using the smooth crack, how do we represent this internal the internal energy of the system? So now let's use the smooth function. So this is this is the total energy, while this is the total energy associated with the formation of the crack. And notice that this integral is a surface integral. Now, using the smooth function, you can write this expression as in this form. So here the surface integral is changed to the volume integral, and here this part is known as the crack surface density functional. So the meaning of this is where they define the crack as a density. Crack is actually a surface area, but in this case we are defining the crack as a density. So since we have defined the crack as the density, now we can convert this surface integral to the volume integral. So when we convert this integral into the volume integral, we don't have to track the crack surface area. So we don't need to know the crack surface area. So because of this conversion from surface integral to the volume integral, the numerical implementation is easier. And also when we are dealing with very complex cracks, so this formulation is much easier to deal with. And now we write we call this the regularized energy of the system. So now the regularized internal energy of the system is the energy associated with the formation of the crack plus the elastic energy stored in the material. So now the elastic energy stored in the material is associated with one function. This function. This function is called the degradation function. So this function would degrade with as there is the crack in the material when the damage occurs in the material. So this function would degrade. What I'm trying to say is that when the material is completely broke, so there won't be any elastic energy stored in the material. So this function would take care of that. And here phi is our phase field order this is a phase field variable. So this ranges from 0 to 1. If this value is 0, that means there is no damage in the material. And if this value is 1, then the material is completely broken. So when this phi is 1, this term becomes completely 0. So when the material is completely broken, there is no elastic energy stored in the material. So notice that this phi is what I have shown earlier. So this phi. So when this phi value is equal to 1, that means that the material is completely broken. And this degradation function has a property that when there is no damage in the material, that is phi equal to 0, its value is 1. And when the material is completely broken, that is phi equal to 1, then this value is 0. So when this becomes 0, the total term becomes 0. And also it has to satisfy the condition that its slope, when the material is completely broken, its slope should be 0. So what this tells is that when the material is completely broken, there is no further degradation in the material. So that's why the slope at phi equal to 1 is 0. If you have any question in between, please stop me. It would be fine for me. Now I'll go to the next slide. Now suppose if is there a question?
No question yet. Go ahead.
Okay. So if we want to incorporate more physics into the system, say like here in this expression we have this critical energy release rate. Imagine if we have a cyclic loading, or if we have a fatigue kind of loading. So with time, it would degrade the fracture toughness of the material. So in that condition, we have to degrade the GC term, the critical energy release rate. So when we apply cyclic loading, this term would degrade. So how do we capture that? We can capture that by incorporating one function, which is the fatigue degradation function. It is given by f of alpha bar, and it is associated with GC. So this expression is given by the this f of alpha bar is shown here, and here alpha t is a energy threshold. This is obtained from the maximum stress. So when this alpha bar is below a threshold, so its value is 1, and once it crosses the threshold, then the f of alpha bar is represented by this function, and this alpha bar t, which is here, this alpha bar t is given by this expression. This is the accumulated local energy of the material. So as this grows and grows bigger and bigger, so this term will become smaller and smaller, and this term is associated with this GC. So as it gets smaller, the GC will also get smaller. So this is how it degrades the GC when we have cyclic loading. And so if we want to not only the cyclic loading, we can include hydrogen diffusion. We can also incorporate other effect of, like, the effect of heat. So all these things we can do. Now let's look at the weak form. So earlier I have shown the total potential energy. So this is the total potential energy of the system. So to get the weak form, we have to take we have to minimize the potential energy of the system. So when we take when we minimize the potential energy of the system, we can arrive at the weak form. This is the weak form for the force equilibrium equation, and this is the weak form for the phase field evolution equation. So this is the phase field phi, and this equation, the whole equation is the phase field evolution equation. And from this weak form, if we expand this weak form and apply the divergence theorem, we can arrive at the strong form. This is the force equilibrium equation, and this is the Craig or the phase field evolution equation. And this Craig evolution equation is driven by this function h. This h is nothing but the maximum local tensile energy. So we can think of like this when we load the material at the material point. So this is the maximum local tensile energy in the material. This H drives the phase field evolution equation, and now we have a couple equation. One is the force equilibrium equation, and second one is this one. So we have to solve these two equations. And how do we solve these two equations? So we use a method called the staggered scheme. In the staggered scheme, first we solve this equation. We get U. From the U, we get the U is the displacement from which we get the strength. And once we have the strength, we can get the local strength and energy. And the local strength and energy is passed to this equation, which is the H, and this drives the evolution of the phase field phi. And from this we'll get phi, and this phi is, and while we're solving for this, we use this phi in this force equilibrium equation. So now let's look at the flow chart of the staggered scheme. So I will explain what is K and what is R, but I hope everyone is familiar with the stiffness matrix and the residual matrix. So since we have two equations to solve, so this one solves for the phase field phi, and this one solves for the displacement. So at the start, we have to initialize the phi and the U. And once we have the initial value, we can get the expression for the maximum local strain energy. And using this, we solve this expression. From this, we get the phi value. And using this phi value, we solve this equation from which we get the displacement. Then we check for the convergence. If it is converged, then we apply the next load step, and the cycle repeats. Now, in the previous page, I have shown here the K matrix and the R matrix. So what is this K matrix and R matrix? Let's have a look. So this we obtain by expanding the residual vector. What is the residual vector that I will show you in the upcoming slide. So by using the Taylor series expansion, we can expand the residual vector as Rn equal to Rn minus 1 plus dou of R divided by dou of U into this U can be displacement. It can be phase field phi. It can be any other field depending on what we are solving. And I have neglected the higher order terms. So if we and we want the residual to be 0. So if we make this residual 0, then this expression can be written as shown here. And here dou of r divided by dou u is the stiffness matrix. So this is the same stiffness matrix that I have shown in the previous slide. So here the k is the tangent stiffness matrix, and here r is the residual vector. So what is this residual vector? Let's see in the upcoming slide. So the entire expression is the residual vector. If you look at the previous slide, so the entire thing is equal to 0, and we are saying that this entire thing is the residual vector. So we want the residual vector to be very small. So the smaller it gets, the better solution we can get. This is the residual vector for the phase field evolution equation. Sorry, for the force equilibrium equation, and this is the residual vector for the phase field evolution equation. And this is the tangent stiffness matrix for for solving this displacement, and this is the tangent stiffness matrix for solving the phase field equation. In the earlier slide, here I have shown that in this matrix, I have shown here we have here k u and the k phi phi. So, but we have this term 0 and this term also 0. So these two terms are 0 because when we are solving using the staggered scheme, when we are solving using the staggered scheme, when we are solving for the displacement, we are taking the phi as a fixed value, and when we are solving for the phi, we are taking the displacement as a fixed value. So that's why when we differentiate the residual vector for the displacement with respect to phi, it is 0, and when we differentiate the residual vector for the residual vector for the phase field phi with respect to u is 0. So because of this, we have 0 here and 0 here as well. Now let's come to the implementation in the subroutine UEL. The subroutine has essentially two parts. One part for solving the phase field phi, and another part for solving the displacement u. And here we also have one UMAT layer. Here, the UMAT layer is just to visualize the result. We cannot directly visualize the solution of the UEL. So the solution from the phase field layer and the displacement layer is passed to the UMAT. So here, no computation is performed, but just to visualize the result from the phase field as well as the displacement layer. So whatever we have calculated from here as well as here is passed to the third subroutine UMAT. So as I have explained earlier in the flow chart, to solve for the phase field phi, we have to assemble the stiffness matrix and the residual vector, and then we have to obtain the local strain and energy from the second layer, and then we can solve for phi. Similarly, here also we have to assemble the stiffness matrix and the residual vector, and then we have to obtain the phi from this layer, and it is passed to this layer. So using the phi from the first layer, we solve for the displacement, and this cycle repeats until we reach the maximum load. So this is how the Abaqus subroutine looks like. So the first part is the this serves as the interface between the Abaqus software and the code that we are going to write. So here they have defined, they have declared some of the variables like A matrix. A matrix. This is the stiffness matrix where we'll pass the stiffness matrix here, and RHS. This is the residual vector. So the residual vector would be passed to this RHS, and here the U can be displacement. It can be phase field phi, depending on what we're solving. But they have used the use U to denote the variable that we're solving. And this the dimension part. This describes describes, as the name suggests, it describes the dimensions of the uh, variables declared here. And here the real star at. So here you can define any variable that you want to define. So these are the user defined variables. So in the UEL, what we are actually writing is the weak form. I have shown the weak form in the previous slide. So once we have to discretize the weak form, and here we have to essentially write the weak form. So here A matrix, in the A matrix, I have written the stiffness matrix. So the stiffness matrix I have shown earlier. This is the stiffness matrix. So this stiffness matrix, this one. This stiffness matrix for the phase field is defined here. Sorry. So in the UEL, we have to define the stiffness matrix and the residual vector. So in the A matrix, I have defined the stiffness matrix, and in the RHS, I have defined the residual vector. And to define this, what are the things we need? We need this BB. BB is nothing but the B matrix, which it is the differentiation of the shape function. So all the ingredients that you need to write this expression, we have to define. So you need to define this B matrix. We have to define the shape function. And stress is once you have the displacement. From displacement, we can get the strain. Once we have the strain, we can have the stress. And here the CMAT is the material stiffness matrix. So essentially, what you are writing in the UEL is the tangent stiffness matrix and the residual vector. And this is for the phase field part. And this one is for the force equilibrium equation. So here we are solving for the displacement, and I have defined the stiffness matrix for solving the displacement, and I have defined the residual vector for solving the displacement. So with this, I want to conclude my my talk, and I have some simulation that I would like to show. After that, I will take. If you have any question, I will take. This is my material system. So this material is a composite material, and here the white region, this is a softer material, and the dark circles, dark circular region, these are the harder material. So I have fixed this material at the base, and I have applied the load on the top. Now I will run this. So you can see that, as I said, this region is the harder material and this is the softer material. The softer material attracts the crack, so then the crack tries to move towards the softer material. And here we have a harder material, and it tries to avoid this harder material. Why it is happening like this? Because it is because of the local stress distribution. And I will also show you the load versus displacement plot. So as the load as the displacement increases, the load increases, and at this point the crack starts to appear, and then the load drops, and we have these kinks on the load versus displacement plot. Yeah, but in this case it is load versus time plot. These kinks are happening because the crack is not going to a straight path. It has to deflect when it comes across the hard region. So while deflating the harder region, so because of that, we can see the kinks on the load versus displacement plot. So this is a region where the crack is trying to avoid the hard phase or the hard region.
Excellent, Sarnat. Let's see if someone have some question. You have something else to show us?
No.
No. Okay. So, thank you, Sarnat, again. If you have any question, please let us know, and Sarnat will help. We will answer your question. If anyone have any question, please open your micro and say. I don't know if you have a backup slide showing the possibility of simulating more than two fields, like what we are doing now. For instance,
Okay.
the mechanical
Okay.
problem, the diffusion problem, and the damage problem. Because
Yeah. We can do that. Yeah.
as Arnald has said, the important thing here is we can solve many differential equations governing different phenomena. So the idea is to have the residual and the stiffness equation for all these partial differential equations, so we can solve everyone in a couple manners and somehow. So we have a couple of questions here. I think Rodrigo and then Briggs.
Okay, hello, good afternoon. Let me answer a question about hydrogen embrittlement. How could we simulate that or put the equations? And also, if we have residual stress, how could we implement that?
So if you want to implement the hydrogen diffusion in the system, then we would have three couple equations. I hope you can see this expression here. We have the force equilibrium equation. The second one is the hydrogen diffusion equation, and the last one is the phase field equation. So now we can solve these three couple equation, and then we can model the hydrogen diffusion in the material.
and he also was asking about the residual stresses. The residual stress, I think you can include it in the beginning of your model, like
Yeah.
constraint value, right?
Yeah. We can include at the start of the simulation.
Okay, as initial state. Okay.
At the initial stage, yeah.
Yeah.
I think also it's possible to try to model the process of introducing the residual stresses, but you can use it at the beginning as a initial condition.
Okay, it's not necessary we include this in the equation. In the equation, we will consider this residual stress in the initial state. Okay.
Yes, initial
Yeah,
stage,
yeah,
initial
yeah.
condition. Okay. I think Luis.
Yeah, I think there's someone ahead of me.
Nathan. So, okay, thank you, Nathan. Please.
Hello, everyone. Thank you for the presentation. So, relating this for the elastic plastic fractal mechanics, taking that it is limiting for the HRR equation, what is the limitation of this phase multiphysics problem regarding the elastic plastic? I'm sorry, related to the stress strain fields.
You are asking about the limitations of the
Yes.
this phase fill method.
Yes, it can be used for
Okay.
ductile materials only for.
Okay. Mm. The some of the major limitation that I am aware for the phase fill method is that it is computationally very expensive, uh, and also you have to refine the mesh where the crack is expected to grow. So this leads to a very high number of mesh elements,
Mhm.
which can cause very high computational cost.
Yeah.
Yeah,
Maybe
and
I
yeah,
can say something. Nathan is also requesting, or he's interested to know about what happened when there is plasticity, because he's talking about the limitation of the common elastoplastic fractal mechanics. So there is actually no limitation with regarding this method has been extended to include plasticity. So Sarna has shown the energy function. We need to include additional term in order to take into account the plastic dissipation that the material is doing where the load is applied. So we need to modify this elastic version to include the plastic dissipation, but it's also possible to do it. We are doing that. We are working on that now. So we can say that in the beginning, there is no limitation to the method to study brittle or ductile problems. Okay.
Thank you. Impressive.
Okay. Luis, please.
Yes, good afternoon. Thank you, Sarnath, Diego, for the presentation. I was just wondering, when you choose the continuous phi function you talked about at the beginning
okay,
of the presentation,
okay.
you are choosing an exponential decay. And I was wondering, what's the sensitivity of the results if you choose maybe a narrower decay or a wider decay, or if you choose a type of function that's not exponential but still decays to zero at infinity? What's the sensitivity of your results on the choice of function, and what guides the choice of function for this type of
Uh,
problem?
yeah, so I have not actually explored different kind of this smooth function. I have used what is mostly used in the literature.
Yeah.
But yeah, I actually agree that yeah, if you have a different choice of function, it would definitely have an effect on how the material respond. But I cannot really comment on, like, I mean, if you use this function, how it will behave, because I have not really explored in that uh, in that way.
Yeah. Okay.
Yeah, what Sarna has done is he has followed what other people were doing in the past. Everyone has chosen this type of function in order to model the phase field evolution. Yeah, I know where if someone is exploring that because in the way that he has it has been selected is working properly, right?
Yeah.
Any other question? No more question? Okay, so the idea was to introduce you to these new capabilities, new possibility to model multiphysics problem. So the idea you need to have, you need to know what is the differential equation that govern your problem. You need to obtain the width form, and then you need to discretize the equation, and then you can implement that in the UL routine, and Abaqus is going to solve the nonlinear system of the equation. So in principle, you can solve many coupled equations as you want, okay? Of course, because he's using now some special strategy to solve the equation. He's using he's frozen some value and then he's solving the other equation. So that is a limitation in order that you need to use a small type increment in order that the solution convert to the same time, to the same place everywhere. Yeah, that I think is one limitation of using is this staggered scheme to solve the partial equation. But with that saying that, I think this open many opportunities to solve different multiphysics problems, including thermal problem, including damage, including diffusion. I motivate you, I encourage you to try to use this in your future work. Okay. Thank you everyone. Thank you, Serna, for your presentation. I will share. I want to stop now the presentation, the recording of the presentation, and I will share it later. Okay.
Thank you. Thank you. Thank you, everyone.
Thank you.